Okay, now spherical coordinates. A sphere in spherical coordinate, well, first of all, okay, can't read my own board, it's too disorganized. Spherical coordinates. Well, here are the spherical coordinates, okay? If you've got a point, rho is the distance from the origin to that point. Now, we've already seen this, but let's just review it. Rho is the distance from the origin to our point. We project that point down into the xy plane, and then take a line from the origin out to our projection point, and theta is the angle of that line segment with the positive x-axis as measured in the counterclockwise direction. Phi is the angle between the y-axis and the segment from the origin out to the point. Okay, so I've made an attempt to sketch the usual diagram. It's not a very good attempt, but we'll have to live with it. Okay. Again, here we have a point rho with angle phi here, angle theta here. Now this rho sine phi is in reference to the length of this side. So let's see what that is. We've got this right triangle here. Okay, right angle here, we know the hypotenuse rho. So if we know one of these two angles, we can figure out this side and this side. So, well, we have phi here, and phi is the angle with the y-axis, or z-axis, which is vertical, and we have this vertical projection line, so that this segment from the origin out to our point is a transversal of two parallel lines, so that the alternate interior angles, this one and this one, are equal. So this angle is phi, so that this side is clearly then rho cosine phi, this side is clearly rho sine phi. So now we know the distance from here to here, and what we're wanting to do is figure out the volume increment. Okay. Well, first of all, let's look down in the plane, because it's fairly easy to figure out the area of this increment in the plane, which is going to give us one of our dimensions of this little volume box up here. Okay, so this distance is rho sine phi. That's the distance from the origin, and we have a delta theta, an increment delta theta here. So by the definition of radian, the arc length here is equal to the radius rho sine phi from here to here, multiplied by the angle increment delta theta, so that this distance here is rho sine phi delta theta. Well, if we go directly up to the vicinity of the point, original point, that's still going to be the width of this side. Okay? Now, as we move up here, this side here is going to be the difference in the rho. This side is parallel to our line from the origin to rho, or very nearly parallel to the extent that our increments are small. Okay, so this side is going to be delta rho, because you're going to have a rho here and a rho here, and clearly you're going to have a delta rho. And then making a similar argument, an argument similar to the one we did here, we have our line segment here. If phi changes by delta phi, then the point is going to move, and everything else stays the same. The point is going to move along an arc of a circle here. Okay? And that's going to have distance rho delta phi. And that's this distance here. Okay? If you put all that together, you see you've got a box whose dimensions are rho sine phi delta theta from this, delta rho, which is simple and easy to see if you have a good diagram, so look in your book, and a rho delta phi because of this. So the total volume of this thing is rho squared sine phi delta theta delta phi delta rho. I also wrote this rho sine phi delta rho, and it's not important, but it is the other dimension of this little approximate rectangle down in the XY plane. But when you move up here, everything stays in the direction of the row vector, the line here. And I'm being a little vague about that, but this is not relevant to any of this. So it's just here to kind of complete the analysis of the distances we have in the picture. That's why I put parentheses around it. Excuse me. That's why I put parentheses around it. I kind of lost my tone there for a minute. Okay. Well, anyhow, there's our volume increment. Okay. Now we could draw pictures and build this up by partitions, but I'm not going to go to that detail. I'm just going to kind of, for time reasons and because I think you can visualize it and understand it. So to do a sphere in spherical coordinates, we have our description in spherical coordinates. Our volume increment is this. So to get the total volume, we just integrate that volume increment over the sphere. This is what comes out of partitioning, okay? And it comes out of these inequalities in a straightforward manner, in a very similar way to the way we could have done it previously if we didn't want to go to all the trouble and get our hands dirty with the partitions. That's an important process, though, so you need to understand it and try to think it through for the spherical coordinates. Okay, so anyhow, phi goes from 0 to pi, so we're going to integrate rho squared sine phi d phi with respect to phi, because we have that sine phi. And then we substitute from 0 to pi, we're going to lose our phi and we're going to get a definite result. And then we're going to integrate that result from 0 to 2 pi with respect to theta. And then the final result from 0 to a with respect to rho. Let's make sure we see if that's an a. It kind of looked like a 0 to me and probably did to you too. Okay, so here's our final, well, here's our first step of the integral where we do the inner integral of the rho squared sine phi d phi. And I could have had the rho squared all the way out here with the d rho, but I just left it where it was. Okay, so we have a negative rho squared cosine phi evaluated between phi and 0. Why? Because the antiderivative of sine theta is negative cosine, of sine phi is negative cosine phi. Well, cosine of pi is negative 1, cosine of 0 is 1, negative 1 minus 1 is negative 2, negative rho squared times that is 2 rho squared. So work it out yourself. Yeah, don't listen to what I said. And see if you don't agree. Okay. And if you don't, well, work it out again until you do, because I think this is right. Then we have to integrate with respect to theta. And I'm not sure why I wrote a d phi here, because we've already integrated with respect to phi. I don't know what I was thinking, but that was wrong, so let's get rid of it. Okay, so, well, the 2 rho squared, it looks a little like a p. There's kind of a, okay, there it looks like a rho. We can bring the 2 out, and we can move the rho squared over here with the d rho. And I know why I wrote a d phi. Because I had a d phi up here. Okay, now let's be clear. When I integrate this, I end up with a d theta d rho, not a d theta d phi. And then when I integrate with respect to theta, I just end up with a d rho. Now I took the rho squared out of this integral and put it over here because rho does not depend on theta. Okay, so anyhow, the integral of d theta from 0 to 2 pi is just theta evaluated from 0 to 2 pi. And that's just 2 pi. So now we have the integral from 0 to a of 2 pi, rho squared d rho. Well, that's an easy integral. We'll bring the 2 pi out. I don't know why the 2 went back into the integral and came back out, but it did. Okay, the 2 pi rho squared d rho. Well, the integral of rho squared with respect to rho is rho cubed over 3. Evaluated between a and 0, and this a looks a lot like a 0 too, so let me make it clearer. And evaluating that, when rho equals A, we get A cubed over 3 times 4 pi. What is that? 4/3 pi A cubed, and that is the valid formula for the volume of a sphere. Okay. Now, if you have a density function or a moment of inertia, you try to, you've got to enter those quantities in the appropriate point, just like we entered the density here, which then multiplied by volume gave us mass.